Yo, Code Pilots! Welcome to part 3 of the Python Masterclass, Data Structures. We've covered arrays, and now we're stepping into the world of stacks. If you're new here, I've explained Python basics and OOP in separate videos. Head to the playlist to get the foundation. Let's dive into this stack of knowledge with excitement. Let's start by understanding what a stack is. A stack is a linear data structure that follows the LIFO principle, last in, first out. Imagine a real-life stack of plates on a table. You place a new plate on top, and when you need one, you take it from the top too. In programming, this means the last element added is the first to be removed. A stack has two core operations: push, which adds an element to the top, and pop, which removes the top element. There's also an optional check, like is empty, to see if the stack has any items. This structure is super useful because it mimics how we often handle tasks, where the most recent action needs attention first, like undoing the last edit in a text editor. Let's explore how this works in detail, and why it's such a powerful tool as we move forward. Why do stacks matter so much in programming? They pop up, pun intended, in all sorts of places. Think about a web browser's back button. Each page you visit is pushed onto a stack, and hitting back pops the most recent page off. In coding, stacks are critical for managing function calls. When a function calls another, the current state is pushed, and when it finishes, it's popped to return to the previous state. Another cool use is checking if parentheses in code are balanced, which we'll dive into later. The LIFO nature ensures a natural flow for these tasks, making stacks a go-to choice for managing data where order of removal is key. We'll use Jupyter Notebook to bring this to life interactively, so let's get our hands dirty with some coding and see how it all fits together. Let's create a basic stack using a Python list in a new Jupyter cell. Type stack equals open and close square brackets and run it to initialize an empty stack. Now let's push some elements. Use stack.append1 to add 1 to the top. Since append adds to the end of the list, it becomes our top. Run print stack, and you'll see 1. Let's add more. Stack.append2 and stack.append3. Then print again. Output is 1, 2, 3, with 3 now at the top. The append method is perfect here because it always places the new item at the end, aligning with the LIFO idea of pushing to the top. To pop, use stack.pop. This removes and returns the top element, 3, and printing stack now shows 1, 2. This simple approach uses Python's built-in list methods. But let's think about why pop works this way and how it fits the stack concept as we build on it. Let's take it a step further and create a custom stack class for more control and clarity. In a new Jupyter cell, type this code. Class stack, def init self equals int a list of empty lists to hold stack items. Def push self equals append item, adds the new item to the top, end of list. Print exclamation mark if you end up putting push. Equals pop item in stack, return self items pop, removes and returns the top item. Else, print stack is empty, cannot pop. Return none. Def is empty, returns len self items equals 0. Def peek, if not self is empty, return self items 1. Returns the top item without removing it. Return none. Now create it with myStack equals stack and test. MyStack push 10, MyStack push 20. Print f popped. MyStack pop. Print top item, my stack peak. Running this gives output like push 10 to the stack, push 20 to the stack, popped 20, and top item 10. The push method adds to the end, pop removes from the end, and peak lets us see the top without changing the stack. This class gives us a structured way to manage a stack, and the print statements help track what's happening. Let's see how this can be applied in a real scenario. Let's dive into a detailed use case, checking if parentheses in an expression are balanced. This is a classic problem where a stack shines. In a new cell, add this code. Def is balanced expression. S is stack. Creates a new stack instance for char in expression. Loops through each character. If char equals where. If it's an opening parenthesis, s.push char. Push it onto the stack. Print pushed s. Stack now its items. If char equals parenthesis, if s is empty. Check if stack is empty. No matching opening. Print found closing without matching s. Unbalanced. Return false. Popped item is s pop. Got the top item. Print 5 popped item stack now its items. If s is empty, for balance, print all parentheses matched. Expression is balanced. Return true. Else, print remaining items in stack. Stack now its items. Expression is unbalanced. Return false. Run it for... It pushes 3 little a's, then pops 3 parentheses matched. Expression is balanced. Output is true. For O, it pushes 2 unparentheses, but only pops 1, leaving 1a, so remaining items in stack. Expression is unbalanced. This process uses the stack to track opening parentheses and match them with closings. If the stack is empty at the end, the expression is balanced, otherwise it's not. This step-by-step tracking with prints helps us see exactly how the algorithm works, making it clear why stacks are perfect for this task. Let's reflect on its importance. To wrap up, we've thoroughly explored what a stack is with its LIFO principle, implemented it using a list and a custom class, with detailed methods like push, pop, is empty, and peak, and applied it to the practical problem of balancing parentheses. We saw how append and pop handle the top of the stack, and the parenthesis checker showed how stacks manage nested structures by keeping track of openings until closings arrive. This depth of understanding sets us up beautifully for the next topic, queues, where we'll see a different flow of data. The interactive Jupyter environment helped us visualize each step, and I hope this detailed dive cleared up any confusion. Let's gear up for more. That's it for Part 3, Code Pilots. You've mastered stacks and their real-world magic. Like this video, subscribe for more, and practice with the stack class and the balancer code. Try it with different expressions. Next time, we'll tackle queues, so stay tuned, keep coding, and see you in the next one.